So my name is Will Lovett. I am a technology manager in the software division of ARM. And so my role is to guide all of the work by ARM's compiler teams. So all of the LLVM and GNU work, and we have a team doing functional safety qualification. And for the first time for me, I get to announce a new product. We normally have like product managers and stuff who do this sort of thing. So I'm going to pretend to be a product manager a little bit, but hopefully not too much. And so the role of technology management is to work as a bridge between what the business needs and what we ask our engineering teams to do. So we work with requirements, and we tend to ask sort of three questions of why would we want to do something, what is it we want to do, and how do we want to do it? And the why is normally a business thing. Sometimes it comes from internal engineering stuff, but mostly it's kind of what does the business need. Then the what is like a negotiation between the business and engineering to work out exactly what the business means and make sure that everybody is aligned about what it is we're aiming for. And the how is mostly an engineering thing, but feeding that back to the business to get feedback is an important part of the process. So I'm going to start. This talk is going to structure itself in similar lines. I'm going to start with the part that looks at why and brings us through to what. So we believe we need a new compiler, and this mostly comes from needs from ARM's automotive line of business. So the next few slides come from the automotive lab, and you can tell because they're really pretty. So the automotive industry is going through a whole load of change where there's three major bits of change of increasing amounts of autonomy in vehicles, from driving assistance features through to fully self-driving cars. Users are expecting more advanced user experiences where you expect your car to behave more like your phone. And more cars are being electrified. And all three of these need a whole load of software. So the lab have got a great stat where a current generation car uses about 100 million lines of code, which is mildly terrifying. And they expect that to grow to like 300 million by the end of this decade. So in order to manage that complexity, and in order to get products to market quickly, which this market demands, you need a software stack that looks a bit like this. Now, I'm not going to go into loads of detail about what this stack looks like and so on, but if you're interested, I thoroughly recommend going to the keynote tomorrow, where Siraj from the Auto Lab is going to be talking through. Is it Siraj or is it you? Both of you, excellent. Are going to be talking through this full story. But the part of it that interests us from a toolchain perspective is shown on this slide. And the slide is a little bit complex, but I'll walk you through it. And this is a view of what development looks like for somebody developing an application for a modern car using the software stack that ARM and our partners want to build. If you look on the left-hand side, you can see that one of the ideas behind this is that a significant amount of development of the code for your car can happen in the cloud, and in a cloud development environment with an operating system and all its associated tools, and individual applications being built inside of that OS. And then later, that same OS and those same applications get deployed to the edge or to your vehicle and execute there. It's helpful, from ARM's perspective, that the architecture that we have in all of our cloud instances is basically exactly the same as the A-profile architecture that's in all of our automotive solutions. So lots of the time, that same code can migrate from the cloud to the edge pretty much flawlessly. Now, in order to do this, you need to build an operating system that's suitable for use in a car, which is not a straightforward task. And there's a project from ARM called SOFI, where we're working with our automotive partners, and a number of other software vendors to work out how to solve this problem in a consistent way. This reminds me a lot of the keynote from Grant yesterday that talked about the kind of early stages of ARM in infrastructure, where everything was bespoke and everything, all software stacks just targeted one piece of hardware. What we're trying to do here with our partners is to get to more similar to where the infrastructure line of business is now, with lots of standards and lots of shared code. And one of the partners we're working with is a company called Electrobit. So Electrobit are a part of the Bosch Continental group, and they last month announced that they're developing a new product that they're calling CoreBOS Linux for safety applications, which is a fully open source operating system that based on Ubuntu that is designed for safety applications, and they're going to provide long-term maintenance of and things like this. In order for that to work, there needs to be a full stack of qualified components. I'm not going to go into the details of all of that stack, but from a toolchain perspective, what you need is a functional safety toolchain for building the operating system itself. Now, we already have one of these. ARM compiler for embedded has functional safety releases, and it would be suitable for this sort of a use case. But you also need a toolchain within that operating system for application developers to build their code with, that uses the operating system libraries, but is also functional safety qualified. And we don't do that today. So that's a new need. And we've decided that this is a sufficiently new need that we want to build a new tool chain. So that's the why and the what. A question? Can we get a mic? Thanks.
So what does mean functional safety in this ecosystem?
So there are a set of ISO standards that define methodologies of working when you're building code that is to be executed on safety critical systems. So if you imagine there is code in your car that controls the car braking system, and it's very important that that code always works and that it satisfies real-time constraints and so on. And there is a set of standards about how you build all the tools that are used to make that code, and how you build the code itself, and how you test all those things, that provides strong validation that the code is going to work as expected in all circumstances. Does that answer your question? Okay, so going back to the previous diagram of the development environment, we can see the platform toolchain is there to build the operating system itself. The application toolchain is there to build applications within that. And then those applications can be deployed into your vehicle. So I'm going to switch tracks for a moment and talk about LLVM for a bit. Oh, question.
Why cannot the platform toolchain be used to build applications? Doesn't it support C++?
It can, and absolutely. We've been developing Linux toolchains forever, right? That's fine, but you must safety qualify that toolchain, which is a very significant effort. So we are choosing to do this on an LLVM-based compiler because that's where most of our development happens, and also there are license reasons why it makes sense for ARM and for our partners. But in theory, yes, you absolutely could make a functional safety version of the platform toolchain. There is.
But isn't the platform toolchain already certified?
I don't believe so, no.
Okay, so I misunderstood that slide, sorry.
Oh, sorry. Right. Okay. Let me. I understand your question now. We already have ARM compiler for embedded, which is a functional safety certified toolchain for embedded development. That's true. We're going to keep that, and that's going to carry on for quite some time. But the new toolchain we're developing is intended to meet both those use cases and will eventually supersede ARM compiler for embedded. But we're coming to that in a moment. Okay, so ARM and LLVM. This is a timeline of ARM's first commercial toolchains in LLVM and how they've progressed over time. I'm going to go into a little bit of detail about each of these toolchains, but the key takeaway from this slide is the progression from fully closed source components on the left-hand side and steadily making our way over to using fully open source components in almost all circumstances for all toolchains from ARM. This has happened over the last 10 years. I've actually been with ARM almost exactly 10 years, so this has been a progression in my whole time at ARM. And it's been great for somebody who loves working with open source code that there's been a shift in that time of ARM's strategy and business model away from trying to monetize software through to viewing software as an enabling function through which we can deploy more ARM-based hardware, which means that the business needs are really nicely aligned with how we want to work, which is putting everything in open source and enabling as much of the ecosystem as we possibly can. So we can start with ARM Compiler 5, which was a fully closed source toolchain for embedded development, and shift from there to ARM Compiler for Embedded, which is our current flagship toolchain for embedded development. It has a significant downstream delta for code gen, and it has a proprietary linker and libraries. Now, that was useful because at the time, that allowed us to inherit some very nice properties in the linker from ARM Compiler 5 that were very useful for things like code size in embedded development, which was a positive. A mild negative is that required some learning on behalf of the user of how to use the linker configuration files, which meant that migration from other toolchains like GNU is not trivial. And I should also mention that we have functional safety releases of this toolchain where we safety qualify both the compiler and the embedded C libraries, and we provide a very long support window for individual releases of this toolchain. Next, we have ARM Compiler for Linux, which is a totally different space. It's an application-hosted compiler aimed at the high-performance computing and infrastructure space. We started with a bunch of downstream code with this out of necessity, because when we first developed this, it was our compiler for the SVE vector architecture, and that wasn't yet public. So we did a whole load of work downstream, and then it took us quite a long time, but we've now got there where everything that we had in that toolchain is now upstream. And as of the last release, which is based off of LLVM 18 and came out in April, there is no code gen from downstream in ARM Compiler for Linux. Now, the linker is easy because it just uses the system linker. It does have some math libraries. We have a product called ARM Performance Libraries, which are closed source. Those got discussed earlier if anybody was in the Ask ARM Anything session. But they are freely available, and the parts that we think people find useful from that, we have upstreamed into a GitHub repo called ARM Optimized Routines, and from there into glibc. So we've upstreamed as much of that as we think is sensible. Then last note on that is that this compiler has a Fortran front end, which was initially a mostly closed source project. We've been working with Linaro and with other partners and with other folks in the LLVM ecosystem on the new LLVM Flang front end. And I'm really pleased to announce that later this year, I expect us to deliver a beta quality release of ARM Compiler for Linux using the LLVM Flang front end. Well, honestly, that's for the whole community. I think that project has gone really, really well. It's great. Okay, so the main point here was that taught us that shifting to an upstream focused development model in LLVM went really well. Then, how am I doing for time? Okay. The next thing I wanted to shine a light on was the LLVM Embedded Toolchain for ARM. So this is back in the embedded space, and this was a project that was initiated by our engineering team, who recognized that with not that much work, we could make LLVM suitable for embedded development on ARM. So we now have a GitHub project, which is a set of scripts for building LLVM in a way that's suitable for embedded development. And we've contributed a bunch of stuff, including linker improvements to make it more suitable for that space, including lots of the code placement features that we had from our commercial compilers, support for multi-lib, which I won't go into what that is and how it works, but if you know what that is, that's fine. And adding support for, adding a runtime library that allows us to support sanitizers like the undefined behavior sanitizer, and also code profiling and code coverage tools. And it's worth pointing out here that one of the benefits we get from basing our tools off of open source LLVM and LLVM components is that when the community works on features, especially things like security features like sanitizers, it makes it much, much easier for us to take those and use them in our commercial tool chains if everything is based on LLVM components. So we provide releases of this also on GitHub. They're completely free. It supports ARM v6m and greater, which means Cortex M0 and greater, basically. And we're working on RNA profile support. It's experimental at the moment, but it does basically work. Okay, so that takes us to now. And and I've already been through why we think we need a new toolchain, so I'm delighted to announce that next year ARM will be launching a new toolchain, which we're using the codename ARM compiler next for at the moment. We have a whole go-to-market process whereby the exact name will be agreed, but you can guess what you think it might be. And so let's take a look at what it will contain. So it will become our new flagship compiler, and over time we expect it to be suitable for the same use cases that ARM compiler 6 is suitable for today, for embedded development, with ARM's current embedded C libraries ported to work with the LLD linker. So it will use the LLD linker for embedded development and have our C libraries. We'd like to look in the future to finding ways of getting our libraries upstream or contributing to some upstream C library, but exactly which one we use and kind of working out one that is suitable for all of our partners is still a work in progress. It will be fully upstream LLVM code gen whenever the upstream will take that code gen. And our typical working model now for all of our development will be to do all of it upstream first and then base our commercial compilers off of that upstream code rather than the other way around, which is great. And then in addition, it will support Linux and real-time operating system hosted development. So we're going to work with Electrobit and other partners like this to work out the subset of C++, for example, that their users need to use and create qualified C++ libraries alongside the C libraries that will be within that operating system as our part of a fully qualified functional safety stack for developing code like this. And the first functional safety release of this, we're aiming to get out in the back half of 2025. So in summary, development of code in the automotive space requires a lot of collaboration. And so we're going to collaborate with partners to develop a functional safety solution for ARM. And this represents pretty much the end, with a few minor bits and pieces left, but we'll work on those, of a 10-year shift in ARM away from developing code downstream for toolchains to doing everything upstream first. And big shout out to the LLVM community, because this is only possible because of how high quality the code in LLVM is. That's all I had. Any questions?
You said Linux RTOS hosted development, and maybe this is an academic distinction, but is that, are people generally expecting to cross-compile to the Linux and RTOS that's running on the car, or are they live inside an instance of that RTOS typing make inside of it?
The detail of how we make this work most of this talk is about the Electrobit Linux distribution. There are other partners who care about other RTOSes, and exactly how we place this compiler in the development flow for those users is a work in progress, and we haven't worked out the details yet.
So it might be a cross compiler, it might be a system compiler. Don't know.
Yeah. But for this use case, it's quite nice, the idea of it being a hosted Linux instance in the cloud that you can work in directly. But the details of that are still being worked through. Hi.
What does the unicorn stand for?
The unicorn is the symbol of software at ARM. It is Mark Hambleton's pride and joy, and it reflects an idea that hardware without software is expensive sand, as he likes to say, and that software development is a superpower of ARM, and finding good software developers is like finding unicorns.
Sorry, can you just remind me what the Electrobit thing is again?
So Electrobit are our company that are a subsidiary of Bosch Continental, and they're working with Ubuntu to build a Linux distribution that will be suitable for use within an automotive system, within a car. And that can host functions of that car within that, and are looking to solve a bunch of the problems of how you make sure that whole stack is qualified for use in safety critical situations. Any more questions? Lovely. Thank you very much.